Hello, today we're presenting our CS225 final project.
My name is Huang.
Hello, I am Tommy Kimura.
I am Danny Lee.
Hello, my name is Taige.
We will begin with an explanation of our proposed goal.
Over the last 2 years, COVID-19 has been an extreme problem around the world. Suppose there is an unknown virus outbreak somewhere in the world just like COVID-19 in the future. How do we prevent the spreading of this virus from happening? There are yet flight restrictions and the virus could spread easily through airlines. In this project, we will try to simulate the spread of the disease with BFS traversal given an origin point A and a destination point B. We will also implement Prim's algorithm to find the path of the virus and find airports that are the most likely to get infected. On top of that, we would like to produce a graphical output of all the airports and airlines, and of course the path of the virus so that we can prevent the spreading efficiently. For this project, we're using the OpenFlights Dataset, and we mainly focused on two subsets provided, the airport dataset and the route dataset. The airport dataset provides information regarding each airport, which will be the node of our graph. Although there is a specific dataset called airlines, this airline subset does not tell us the source and the destination of each airline. Therefore, we decided to use the route dataset, which contains the source airport ID and the destination airport ID. And we will use these IDs to identify the airports. Each airline will be an edge connecting our nodes, which is our airports, and we will explain how we store these nodes and edges. We believe that we have met our proposed goals and discovered some very interesting results. Let us show you from the beginning of our development.
The data is stored in .dat files, and we wrote a few functions in read from file files to process this data. We first split the file into strings by line, then we split each string into a vector by comma, and lastly, we remove data from this vector that we don't need. Because of the different structures, we have different functions to remove unnecessary data for the airport file and the route file. These two datasets are large, and there are many lines that have incomplete data, and we will process these exceptions in our graph constructor. Now I will briefly illustrate our data structure. We have created different classes. The most important class is the graph class. This graph class takes in non or two string inputs that represent the directories of the airport and route files, then calls the functions from read from file to process this data, and lastly use the vector of string as an argument to create pointers to the airport objects. To ensure that we pass the incorrect data, we have an if statement that checks whether the data at each index is what we wanted. For example, if we get a string or a blank for the airport ID, we will ignore this line and ignore this airport. Each airport object has a unique airport ID and contains a list of destinations. Each destination represents an airline from this airport to the destination airport. This is similar to an edge list. We first consider writing airport and airlines as structs in our graph, but we soon realized that we need to access these objects explicitly in our traversal and mapping algorithm. Therefore, we wrote them as separate classes.
Besides the graph classes, we also implemented our BFS traversal separately. We have a grid traversal class as a parent and the BFS class as a derived. This is very similar to the MP traversal assignments we did. During each iteration, our BFS traversal will add all the destinations of the current airport and mark the height of each airport as 1 plus the height of the source. This height will be used later in map projection. From the offered algorithms, we chose to implement Prim's algorithm to find the shortest path from the origin point A to the destination point B. We are predicting the transmissibility of the virus, and since the virus is more likely to spread at airports with more airlines, we decided to use the number of airlines at each airport as the weight between the two nodes. With the two datasets, we decided to project the data onto a roll map PNG. When we initialize each airport node, we store the airport's latitude and longitude as private variables. Then we wrote helper method in graph.cpp to convert these geographical coordinates into image coordinates. We have offered two types of projection. One projects all the nodes and vertices regardless of the starting point. It is just a pure representation of the entire graph. Another one reflects on the transmissibility of the virus. Airports that are closer to the origin will be red, and airports that are far away will be green. When implementing map projection, we realized that mapping the nodes to their locations has challenges. An interesting one is that the globe is not a perfect circle. It is an ellipse. Therefore, the rectangular map image does not really match the coordinate that we got, and the error is very obvious as the latitude increases. To address this challenge, we added a multiplier to scale the coordinates, and this eliminated about 90% of the error.
And now I'm going to demonstrate our code. We wrote a make file so anyone can just run tests with simple lines, or you can simply type in make, which produces final project, and you can enter your own inputs. In order to execute final project, you need 4 inputs. The first 2 inputs are the directories of your airport and airline files and string, and the last 2 inputs are the IDs of your source airport and destination airport, both in integers. Now let's run this program with full datasets. The program would first generate a graph object and project this graph to an image file called mapgraph.png. In this image, we can see that nodes are projected to their exact locations, with a few exceptions for the nodes that are near the poles, and this is due to the challenges we mentioned earlier. Then, we will implement Prim's algorithm to find the minimum spanning tree that has the origin airport as the root and the destination airport as the goal. In fact, the Prim algorithm in our function is not a full Prim search where a minimum spanning tree is found. We stop the algorithm when our traversal reaches the destination. It still makes use of a vertex set and an edge set for implementation. Then our function prints the airport that experienced virus infection and projects this path to mappath.png. Subsequently, the program initializes a BFS object, and we let it iterate the entire graph and mark the height. Lastly, we project another image called mapgraph_trans, which demonstrates the transmissibility of the virus at each airport. The origin point is red, and destination airport that have direct flight with this origin have the highest concentration of redness. And as height increases, or the distance from a node to the origin increases, the color of the node turns to green.
When we discover the virus at a destination airport, our program allows us to find all the airports that needs to be cautious of and predict the future paths of the virus for precautions. And we have a visual graph to help us better understand the behavior of the virus. Even though that we did in our project is not able to produce the most accurate prediction, we can still use it to estimate the overall result and make the path of the virus predictable.
We have a better understanding of graphs and discovered many interesting things about it. We discovered that even if 2 airports are geographically close to each other, there's the possibility that the virus will never arrive at this airport when there's no edge connecting them. Of course, the airline is not the only way to spread the virus, but this result still surprised us, since we thought the surrounding airports would definitely have higher chances of getting infected. We think that this no-edge graph is very interesting.
It has been a great honor working with my group members under such effect of COVID-19. Everyone participate and contribute some way in this project. And I'm glad that we can work something out related to the society and by using what we learned in this semester.
I am so glad to work with other group members. They are reliable and trustworthy. Besides, the result of this project also surprised me because we find something that unexpected. It is a great experience to conduct this final project.
This is a fantastic project experience from which I've learned a lot about datasets. Being able to implement what we learned this semester to work on something meaningful also makes it a great practice. I enjoyed working with my teammates and now have a better understanding of how programmers work as a team. Thank you all for this great semester and hope you all have a great summer.
I feel like the final project is a very interesting coding experience. It feels very much like an MP, but it's unguided, and we are able to implement, our goals through our code. And we also get to make use of the various C++ technique we have learned throughout the semester. So it's definitely very meaningful to me.